mobile phones. Before that, I worked for Siemens. So we've also got some people online. Welcome to all of you folks online. Hopefully you can hear me, and hopefully you can see the slides and everything. So title of this presentation is Navigating the Verification Maze. And the idea is to just give a overview, really, of all sorts of different, I'll use the word random, but not, I haven't rolled any kind of dice to choose them, different techniques in verification. So I've tried to put a different spin on it to how you would normally expect to see it. There's probably perhaps more code than you're expecting. So I'm going to show lots of code, because quite often when people do overviews like this, they don't show code and they talk in very general terms, and it doesn't really, give you a feel for what the thing that we're talking about actually is. So we're talking about navigating the verification maze. Here is the verification maze, and you can see lots of techniques which are in the white writing on the blue maze, and I'm just starting my stopwatch here to keep me on track. So those of you online can't see me, but that's what I'm doing. And the red writing is different technologies for doing verification, most or all of which we're going to talk about. So verification is important. This is a slide, similar slide you've probably seen many times. There's a figure at the bottom there. 70% is the proportion of the project that you might spend on verification. I think that's just a made-up number. The point is, it's a lot. It's important. You're going to spend at least as long on the verification as you are on the design. So some of the examples that I'm going to use a piece of IP that I didn't design, and open source IP, which is a memory that sits on a bus called a wishbone bus. And so you'll see that coming up in several examples. And just in case, I'm just covering my back really, that's the copyright notice that came with the IP. You're supposed to distribute copyright notices with open source code, so I'm not sure what you're supposed to do when you talk about it in presentations, but just in case, there is the copyright notice for the IP that I'm going to be talking about, using as an example. And it sits on this thing called the wishbone bus, which is quite a powerful bus. It's got all the usual signals that you expect to see, address, data, and so on, and then lots of control signals, and you can have multiple masters as well as multiple slaves. So it's a proper big, powerful bus, and that will become relevant at some point today. So navigating the verification maze. We're going to navigate a maze. It would be useful to have a map. So here is the map. This is what we're going to be talking about this morning. So it's a breakdown of different ways of doing verification and different techniques. And we're going to start with hardware, because particularly if you're designing an FPGA, one thing you could do is just program the FPGA. I would highly recommend you don't do that, because it takes quite a long time for the synthesis to run, for the FPGA software to lay out the FPGA, produce the bit stream, and then you get this piece of black plastic on a printed circuit board, and it's difficult to tell what's going on. It's difficult to debug and so on. But people really do that. I teach VHDL. We have people coming on the course that that's what they do. They don't do any verification at all. Don't do that. Another thing that you could do is use emulation and prototyping. It's not really the subject of this talk. I'm just mentioning it for completeness, really. So the EDA vendors will very, very happily sell you very impressive, I was going to say expensive. I expect it probably is, but I don't know. A powerful kit that you can use to verify your chip, your design. So there's what's called emulation, which is specialist processors that run your simulations very quickly. And there's what's called prototyping, which is basically these things that you can see on the slide here are like giant FPGAs, or some of them are. Don't ask me which ones are emulation, which ones are prototyping, but a mixture of the kind of thing. And actually, just to go back a couple of slides, the electronics in the boot of my car there is actually a prototyping system from one of the EVA vendors. So you can do that, but what we're really concerned with is software. So by software, I don't mean writing software that runs on a CPU. I mean using your computer to verify your design. And by far the most common technique, and most of what we're going to be talking about today, is what I've labeled as dynamic here, dynamic being the opposite of static, where we're talking about running some kind of simulation. So with a simulation, you're executing the code. You're executing the code in your design itself, and you're executing a whole bunch of other code, which is the test bench, basically. And the test bench has two main jobs to do. The first one is to supply inputs to the design under test, and the second one is hopefully to check that the design under test is outputting the right thing. And a basic test bench would probably be what is called directed. And so a directed test is where you decide what inputs to give to your design under test, hopefully in relation to the specification. So the specification might say, specification point 1, 2, 3, it must do this when this happens, and you would write a specific test to do that, and that is called a directed test. And the other kind of testing is what's called constrained random testing, which is where instead of specifically writing a test to do a certain thing, is instead you would set up random scenarios with your design under test, and more on that story later. So here is a basic test bench. So our design under test is at the bottom there. You can see it says WB RAM at the bottom of the slide. That's the memory that I talked about 5 minutes ago. And the rest of the test is providing some inputs to that. Now, this particular test bench is written in Verilog. I'm going to show you on the next slide exactly the same thing in VHDL. The rest of the presentation, some of the stuff will be in Verilog, some of the stuff will be in VHDL. In most cases, it matters in the sense that what I'm talking about can only be done in one of those two languages. And when I say Verilog, I also mean SystemVerilog. And so here, what's going on is a very basic test. And even if you don't know Verilog, hopefully you can get something out of this. So we've got like a sequence of things to do. So we're doing it sorry, no, we're not. We are waiting for the rising edge of the clock, for 3 rising edges of the clock. So we wait a little bit to get going. And then these various signals like WB psych, and WB STB, and DAT, and all of that, those are inputs to the design under test. And we're driving them at specific values at specific times. And then we're doing a read. The first one is a write, and then we're doing a read. And we're just manually, the key point is we are manually driving the inputs to our design under test to make it do, as you can see in the comments there, a write and a read. And uniquely in this presentation, I've done the same thing in VHDL. So if you're familiar with VHDL, here is exactly the same thing in VHDL. So we're starting by rating for 3 edges on the clock, and then you can see just with a different syntax, we're doing exactly the same thing. We're manually driving the inputs to the design under test. Now, caveat, I manually translated this slide, which I'm pretty sure is correct because I took it from code that I'd executed, manually translated it to VHDL, and I can see at least one mistake on it. So this code has never been executed. So don't think that doulos don't know anything about VHDL. We do, but this is manually translated in Microsoft PowerPoint, not in any kind of VHDL aware environment. So I can see one mistake, see if you can see any more. But you can see it's exactly the same idea. The instance, the thing we're testing is at the bottom, and you can see the code is very similar. And how do we know that the design under test is doing the right thing? Well, in a very, very basic test bench like this, and this is extremely basic, in my opinion, too basic, we would fire up some kind of waveform viewer and eyeball the waveforms. And this is the kind of thing that you might do when you first design something. So you just want to do some kind of sanity check, some kind of smoke test to make sure that your design really or is vaguely working. Particularly if you're handing it over to someone else to do the real verification, you don't want to hand over rubbish. But looking at waveforms is a bad idea unless you're debugging. So yeah, great for debugging, great for finding out why your design isn't doing what it should, but not for the actual assurance that your design is doing the right thing. Because it's error prone. You might miss something. How do you know the next time you run it that you've checked all of the things you needed to check? It's time consuming and so on. So a much, much better idea is to make your test bench what is called self-checking. So I mentioned this a few slides ago. Not only should your test bench be generating the inputs to the design under test, it should be checking the outputs as well. So you can see here very similar code that you saw 3 or 4 slides ago. We've got just the read here, and if we're doing a read, and remember the design under test is a memory, so stuff coming out is going to be the read data, and so we need to check it. And you can see at this point we've got this statement assert, which is doing the checking. And that's okay, that's better. That's better than what we had before, because we don't have to eyeball the waveforms, which is time consuming and error prone and highly unreliable. Now our design can tell us when our test bench can tell us when our design does the wrong thing. So that's better. But a disadvantage of this is it's very hard to maintain. You do something ever so slightly different at the top in the code where the ellipsis is at the top of the slide, and suddenly it'll break the check. So let's move on to a technique called transaction level modeling. And with transaction level modeling, instead of generating the inputs to the design under test manually, we generate a stream of something called a transaction. And a transaction is something that the design under test, I'm going to say DUT, something that the DUT can do. It's our design under test, our DUT is a memory. So what can a memory do? Well, you can write to it, you can read from it. There are 2 transactions, a write and a read. And with our simple memory, you can write some data to a specific address, and you can read a specific address. And of course, you want to check that the right data comes out. So there are the 2 transactions for our DUT. Whereas if you had some other kind of DUT, like a microprocessor, perhaps an instruction would be a transaction. So an add, a subtract, a jump, whatever your CPU, your processor is doing. Other systems will have other transactions, packets, symbols, whatever it is that your DUT does. But it's some kind of high-level representation of what your DUT can do. And it's probably an atom as well. So possibly packet was a bad example because packets tend to have stuff inside them, but it may be a packet. And this is an extremely powerful technique. Just changing this thing is really, really powerful, as you will, as I hope I will demonstrate. So Obviously, we need to represent this high-level abstract thing in some way. And we're going to start by calling what are called tasks in Verilog. In VHDL, they're called procedures. So if you know VHDL, not Verilog, it's the same thing. And obviously the DUT doesn't understand that. And so we need a component, a piece of our test bench that translates between this abstract software-y thing called a transaction and the actual ones and zeros that the DUT understands. And that thing is often generically called a BFM, a bus functional model. And there are different kinds, and I like the terms driver and monitor. So the one on the left of this diagram, you might call a driver. It's translating the abstract transaction, the concept of a write and a read, to the actual ones and zeros that does a write and a read. And the BFM on the right is doing the opposite. So you might call that a monitor. So it's monitoring the outputs of the DUT and translating them back to some abstract representation of the same thing. And why? Well, one thing you certainly might want to do is check that the transaction is correct. And as we'll see shortly, it's much better to check a transaction. It's much easier quite often to check a transaction than to manually check the raw outputs of the DUT. So let's implement a basic transaction-based test bench. And as I've just said, we're going to use tasks. So task is like a subroutine, if you're not familiar with Verilog at all. So we're going to call these tasks, and the first task does a write, the second task does a read, and you can see that the code on the board, the code inside each task, is very similar to the code that I just showed you 15 slides ago, whatever it was. And so we're manually, now we can't avoid it, obviously, we're manually driving the inputs to the DUT. And you can see at the top there, we're driving the WBADR, which is the address input, with the input to the task, and we're driving WBDAT, which is the data input, with the data that's input to the task. And in the case of the read, we're sampling WBRDT, the read data, out of the RAM and outputting that from the task. So what do we do with these tasks? Well, we need to call them, obviously. So here is some code that calls the tasks. Most basic of basic tests that we could do is write some data to one address in our RAM and read it back, and then check that the data we read back is correct. And you can already see that this check is more robust than what we had before, because we don't really care when we check it. The read is doing the read and it's outputting the data that was read, and it's all pretty self-contained. We could easily stick in more writes and more reads into this test and to check the output from the reads task whenever we're good and ready. So the previous really basic low-level test bench was really vulnerable to the slightest change everything by one clock cycle, and suddenly it breaks everything because the DUT is outputting something one clock cycle later than last time, and the check was done at time 1, 2, 3, 4, 5, and now it's being output at 1, 2, 3, 5, 5, or whatever. Whereas now we're much more robust to that kind of thing. And also, it's really easy to see how you could write other tests. The low-level stuff, the nitty-gritty, is hidden away in these tasks. And so if you wanted to do a more robust test, a better test, fill up the RAM completely and then read it all back, something like that, you could easily do that. You could easily stick the write and the read in some kind of loop and do that. So you can reuse the stuff in the tasks and write more complicated tests and other kinds of tests really, really easily. And that's another real big advantage of using transaction-based verification. And I keep using this word test. A test is what a verification engineer would call a simulation run, basically. So you're likely to have one or a small number of test benches and many, many tests, many different programs, for want of a better word, that call these tasks in different ways to test different things. So, okay, that was what was called a a directed test, as I mentioned 20 minutes ago, we decided what we want to test. And just to go back a slide, the specification perhaps said, if you write something to an address, you need to be able to read it back. There's the test that tests that requirement. But there's an awful lot of advantage, as we will see, to adding some randomness to this. And so instead of doing directed tests, instead of doing a specific thing that we thought of, we generate random inputs to our DUT. And this is a really, really powerful idea. The main reason is because it thinks of things that you didn't think of. Let us suppose that our RAM had a bug in it. It doesn't. I'm not going to try to diss the guy that wrote the RAM. It doesn't have this bug, but let us suppose it had it. And the bug is this: if you read a location again, you get 0 instead of what you're expecting. So the read is somehow corrupting the address. You might not have written a test to have checked for that. Unless you'd specifically thought of it, you thought, well, I need to do a read again to make sure that I read the same thing again, then you probably wouldn't have thought of it. The sort of tests that people often write to test memories wouldn't have found that bug. Whereas if you're randomly doing reads and writes in a random order, sooner or later, that's a really important point, sooner or later, you are going to read a location again that you haven't written to in between. Hooray, as long as the data wasn't 0, you found the bug. So that's the main advantage of random testing. Other advantage is that if you've got enough computers and licenses and so on, you can be running simulations and it can just be churning away, testing your design as well. So that's good. But there's no such thing as a free lunch. What is the disadvantage? Well, the first disadvantage is it's harder to check that the DUT is doing the right thing. Because with a directed test, the test you saw 3 slides ago, we wrote some data to address 0, and then we read it back and we know what data we're expecting. Whereas with a random test, how do we know what the design under test is going to do? And so one way of doing that is to have some kind of high-level model of your DUT. So what you do is you give the same inputs to the DUT and the high-level, what you might call the reference model, and the outputs of the reference model, the golden model, are the expected outputs of the design under test. And so the checking is just comparing the two. That's easy to talk about and visualize. You do need a high-level model of your design under test, of course, which you might not have. Sometimes you do, because you already have one as part of the design process. So you need, for random stimulus, you need what you would call a stimulus independent checker. It needs to work for anything that you throw at the design under test. And that is not, might be, but it might not be trivial. Next problem, and this is the one I alluded to just now, how do you know when you've tested your design? If you're doing a directed test, you've got all of these requirements, hopefully numbered in your specification. You write a test to test this, you write a test to test that. If you're just throwing random stuff at your design of the test, how do you know what you've tested? Have you tested everything or not? And the solution to that is something called functional coverage. Functional coverage, you create what is called a coverage model, which is an electronic representation of all the requirements in your specification, like a checklist. And what you're basically doing is saying, have I seen one of those? Have I seen one of these? Have I seen a read? Have I seen a write? Have I seen a burst read, a burst write? Have I seen this CPU instruction? Have I seen a jump, a load, a store, whatever it is that you're doing? And if you haven't seen all of the things, then if your design under test hasn't done all of the things it needs to be able to do, then you haven't tested it, basically. So that's something else that you need to do. More on that story later. And then what you'll find if you do this is that your coverage will not be 100%. There will be things missing. There will be things that your design has not done. And so what do you do about that? well, you could run the simulation for longer and you would probably get better coverage. But you will also probably find that there's a limit and that you could simulate for a year, 100 years, till the heat death of the universe, and you never get 100% coverage because some things, some scenarios are just not getting generated. Their probability of being generated is 0. And so you've got an iterative process where you need to change how the inputs are getting generated. Hang on, I thought you just said they were random. How can we influence that? Well, when I say they're random, they're not completely random. We're not just putting noise into our design under test. What we're doing is giving it a random stream of sensible things to do. What's a sensible thing to do? What's another word for that? A transaction. And so we're going to generate a stream of random transactions. And the difference between generating a stream of random transactions and just completely random inputs is that the space that we're picking random things from is constrained. It's smaller. We're not going to do anything. We're picking from the set of sensible things. We might put errors in. We might give a packet with an error in or something like that. But even a packet with an error in is not just noise. So we might have got however we do it, the way that we're picking these random transactions, these random sensible things to do, we might have got that wrong, basically. And so there's a loop where we have to correct that. So in some languages like SystemVerilog, this kind of functionality is built into the language, but it doesn't mean you can't use other languages as well, as we will very shortly see. So here is a random test, and we're using the same two tasks as we had before. So we're calling our write test, we're calling our read task. So just to go from the top, this is now SystemVerilog, if you're observant. So we're going around 100,000 times. Sorry, no, we're not. 10,000 times. And is that enough? Well, we'll need to collect some functional coverage to know. But we're going around a large number of times. And you can see that it doesn't matter about the syntax here. If you don't know SystemVerilog, if you don't know any hardware description language, you can see by the word random appears on the 4th line down, we're picking a random address. And you can then see on the 5th line down, we're choosing a random number between 1 and 0. We're flipping a coin, basically. And if it's a 1, then we are generating some random data and storing that in an array. More on that story in a second. And then we're writing that random data to that random address. If the random number was a 0, was not a 1, basically, that we picked, we do a read instead. We don't need to generate any data to do that, but we've already generated a random address. And so we do the read, and then you can see that assert statement is comparing the data that we read out of the memory with the data that we stored in the array. And so a couple of things to say here. You can see we're doing randomness. Now we're randomly deciding whether to do a read or a write. You can also see that we've got this array. And this array is the reference model. It's the golden model of our design under test. So if you think about it, an array is just like an abstract high-level model of a memory. Memories have address buses and write enables and low-level stuff. They're made out of transistors. But an array is just at an abstract level the same thing. And so the array is the model, and you can see on that assert statement at the bottom that we're effectively comparing what came out of the design under test with what is coming out. I'm doing bunny ear quotes, you can't see that online, of the reference model. And the other thing to say, another thing to say is, because we're using transactions, look how easy it was to write a random test based on those two tasks that we wrote earlier. If we were still at the stage where we were manually inputting 1s and 0s, we would be finding this hard to do. So functional coverage is a way of finding out what your DUT has done and what it hasn't done. And the example here is the SystemVerilog language. And this is a construct called a cover group. This is a concept called a cover group. We have some people online as well. A concept called a cover group, which is a container of something called a cover point. And a cover point is a probe, basically. And so when I mentioned this a few slides ago and said it's an electronic representation of the specification, that probably sounded very grand and very abstract, but actually all we're doing is recording the value that variables had as our simulation runs. So it might seem very grand and very abstract, but as long as you choose the variables carefully, you can do this grand abstract thing. So you can see this example here, we're probing a variable called opcode. So if the DUT were a processor, we need to make sure we've executed all the instructions to make sure we've tested our CPU properly. Then we need to make sure that opcode has had all the values that it should have, for example. So basically what you do, and there's a lot more to this, of course there is, this is only a taster, but what you can do is you can see what values each of the variable has. Perhaps you're interested in each individual value, which you probably would be with a CPU opcode. You literally want to check that you've tested all of the instructions. Or if it were like a data input to a multiplier, for example, you're not interested in literally every value. You don't need to test that it can multiply 17 and 18 and 19. But you would want to check that you could multiply small numbers, big numbers, negative numbers, positive numbers. And so you would design these histogram bins, the categories, to fit those. And you can code all of that up in SystemVerilog. And then your simulator will tell you, which values of those variables have not been hit. That's the jargon. And so you can see what's missing from your test. There's also something called code coverage. This is something that's been around a long time. If you haven't executed all of the lines of code in your design, you haven't tested it properly. So it's a sort of more basic thing, but it's necessary but not sufficient. If we haven't executed line 1, 2, 3, then you haven't tested line 1, 2, 3. There's part of your design you haven't tested. But something that's really important to point out, both with this idea of code coverage, which your simulator can do, and what's called functional coverage, is that just because you've done the thing doesn't mean it's right. The checker is still important. Yes, you needed to have tested, you've done a read, a write, a jump, a store, whatever it is you've done. You also need to check that that's happened correctly as well. So the next thing we're going to talk about is some methodologies. So I've talked about some general techniques, but we started implementing them ourselves. That code that I've shown you so far, I just wrote myself. There's nothing fancy about it. But rather, you could see that if you're doing this for real on a real project, then it's going to take a lot of time to generate all of this from scratch. Much better idea to use a methodology. And so you could make up your own methodology. So here's the part of the test code from that open source RAM. So this is the test bench that you get with it, that the guy Olaf that wrote this test bench. You can see the RAM is instantiated 4th line down there, but you can see a lot of other more abstract looking stuff that is basically doing a similar thing to what I was showing you. So we've got some kind of test here that's meant you can see that it's doing high level things by calling high level tasks and so on. And so, yes, you could make up your own methodology, but probably a more sensible thing is to use somebody else's methodology. So I'm now going to talk about 3 different methodologies. 2 of them are in VHDL, 1 of them is in SystemVerilog. And the first one I'm going to talk about is called OSVVM. And OSVVM is an open source methodology. It's developed by a company called SynthWorks in the US and Oldec, one of the EDA companies. As I've just said, it's open source, and it consists of various things. I mean, you can call all of these methodologies testbench Lego, basically. So you get what is called the VHDL verification framework. Actually, that's the most Lego bit. It's how to design different pieces that fit together. So the BFMs that I was talking about earlier, that would be a driver, a monitor. How do they talk to each other? How, in the same way as Lego bricks fit together in a standard way, how can we design pieces of test bench that fit together in a standard way? Drivers, checkers, etc. The verification utility library is just a library of useful stuff that is useful for designing test benches, randomization, coverage, logging, because randomization, you can generate random numbers in VHDL, but it's not really very powerful. So OSVVM adds an awful lot more stuff to that. There's no functional coverage at all in VHDL, so it adds that. And then there's some other stuff as well. I guess there's the next one down is worth talking about. There, you get supplied with a bunch of bus functional models, basically, that do standard methodology, standard protocols, so AXI, Ethernet, etc., etc. Because a big advantage of this idea of transactions and using a methodology is, of course, you can get pre-designed test bench IP. If your chip has a certain interface on it, you need a corresponding BFM, and it'll just work with any chip that has that, any design that has that interface on it. So there's a bunch of packages, basically, that there's one for generating random numbers, one that deals with coverage, outputting messages, checking things, generating clocks, all sorts of different jobs you can see in this table that you can use for, that's going to help you basically put a test bench together. So if we look at some actual, oh no, sorry, apologies, there's I missed one. So here's a diagram of the verification framework parts. This is the test bench Lego idea. So what I've been calling a BFM or a driver or a monitor, this methodology calls a verification component, VC. So those VCs on those diagrams are the BFMs. They are generating the ones and zeros that the DUT understands. And this block there that says test control is the test. We'll look at that in a minute. So one thing that you get with OSVM is OSVVM is some standard transactions. So if you think about it, many systems have transactions that need addresses and data and whether they're a read and write and things like that. And so this methodology actually has a transaction for any like bus system or memory or anything like that. And there's another one called streamrec type, which is for some other similar but generic type idea, some kind of streaming idea. And notice these are in I think I said it's VHDL. This is a VHDL methodology. So the code I'm showing you now is VHDL. That instead of calling a procedure to represent a transaction, we're using a VHDL record type. So it's a different software engineering construct is used to represent this abstract thing called a transaction. So here is our test bench. So we've got, we'll ignore the thing at the top because that's just detailed VHDL, but going further down, well, it's the connections, it's a package of connections. But going down, you can see we've got the design and test here. So, and that is connected to different signals inside this package at the top. And then we've got it's actually a concurrent procedure call generating a clock, and another concurrent procedure call generating a reset. And so that's just IP that you get with OSVVM. And then we've got this component called the manager. That's the verification component itself. So that is a wishbone bus functional model, a wishbone driver and monitor. And then in the corner there, it's the same file as all the rest of the code, but it didn't fit on the slide, so I've just moved it to the corner. But it's all the same entity and architecture. It's all the same file. That's the test. That's the test controller. So the thing in the bottom right is outputting transactions, and the thing in the bottom left is receiving them. That's the BFN, and driving the ones and zeros into the DUT. And then here's the test. Well, actually, there's two slides showing the test. We've got two concurrent processes here. You don't have to have this. It's just the way that this is organized. I just adapted some code that I found. And because VHDL is multi-threaded, we've got a thread here, a process that's doing the housekeeping, basically. You can see it's opening a transcript. It's waiting and closing a transcript and things like that. And these are procedure calls to IP that comes with OSVVM. So you can see that it's giving you lots of useful stuff that you can build your test bench out of. And concurrently, because you can in VHDL very easily, we've got the actual test going on here. So if you look here, we've got about halfway down, there's a call to a write procedure and there's a call to a read procedure. So those are not the procedures that I showed you 20 slides ago. These are procedures that come for free with OSVVM, but you can see that it's doing exactly the same thing. So we're doing a write, we're doing a read, and then the alert if not equal is another procedure call that you get for free with OSVVM that's doing the check. So the key point is we're doing exactly the same thing, but we're doing it in VHDL this time, not Verilog, and we're using a methodology. We didn't write the stuff on this slide, we'd have to write ourselves, but the stuff behind the scenes, the lower level stuff, we got for free. And that's the key point. And it's also important that this is in VHDL. This only works for VHDL. OSVVM is open source VHDL verification methodology. The reason why I say that is that there's a different methodology that I'm going to talk about in a minute, which works for SystemVerilog, which is called UVM. So the next methodology I'm going to talk about is the rival, if you like, to OSVVM, which is UVVM, Universal VHDL Verification Methodology. It's not the same. But it's the same idea. And so it consists of test bench Lego, again, a standard way of creating and joining together pieces of your test bench, and it consists of a whole bunch of useful packages with lots of useful things in to make it easier for you to write a test bench. And this one is developed by a Norwegian company called Logic, and it's open source again. And just like you saw last time, you're going to get a sense of deja vu here because they are very similar. There's a whole bunch of things that it can do, just like OSVVM can do. So logging messages, handling alerts, generating random stuff. It does coverage as well, but I don't think I put that on the slide, should have done. So it does coverage, string handling, just all sorts of useful things that you would need for writing a test bench. So if we have a look at the code for that, you can see it looks pretty similar to what we saw before, but this time it's UVVM rather than OSVVM. And this is the test harness. So this is just how we wire up the different components. So we've got like a controller that you just need for UVVM at the top. So we've got an instance there. Then we've got the design under test. exactly the same design under test as we've had before. Then we've got out what UVVM calls a VVC, which is our BFM again. So again, there's you can see from the name that this is a wishbone. Remember, that's the name of the bus. So a wishbone BFM, it's just standard. It just comes for free with UVVM. I didn't have to design that myself. BitVis is the company that originally developed UVVM. That's why it's called, it says BitVis there. And then you can see that we've got our reset generator, which we haven't used any IP, and a clock generator where we've used another standard component that you get for free with UVVM to generate our clock. And so there's our test harness, this is often called in verification engineering, and here is our test, and you can see it's the same thing again, but this time done using UVVM. So we're controlling messages at the top, we're outputting messages, where you can see halfway down in green, we're calling a procedure called wishbone write. I didn't write that, it came for free with UVVM, but it does exactly the same thing as that task that I showed you 30 slides ago. It probably is now. And then you can see we're waiting, and then we're doing some kind of read, as you can see, and then we're outputting stuff to the log file or the transcript window and so on. It's the same stuff again, but the advantage of using a methodology is you don't have to design it yourself from scratch. And then we're going to look at one more methodology. This is much bigger and much more complicated. So we sell training in UVM, and we have 6 days of training. You don't have to get, the training course isn't 6 days long. The standard training course is 4 days long, but I'm telling you that partly as an advert, we sell training, and partly to just give you an idea of the complexity of this. It wouldn't take you anything like 4 days to learn OSVVM or UVVM, but you spend 4 days learning UVM, and there's still 2 days to go if you wanted to learn more. So much more complicated, many more slides about it. So UVM is a IEEE standard. It's for SystemVerilog now. It's enhancing SystemVerilog, and SystemVerilog is a much more powerful abstract language than VHDL, and so we've gone up a step now in complexity. This is serious software engineering here, but it's also much more powerful, of course. So it's intended to be used for random coverage-driven methodology, but you can do directed tests in it as well. And I did have a customer a couple of years ago that specifically wanted to do directed tests in it. So it's an IEEE standard. All of the all of the EDA vendors support it. So here's a block diagram, and you can already see it's more complicated. There's loads of stuff going on here. You can see in the corner, the bottom right-hand corner, we've got these keywords monitor and driver. Talked about those already. The driver is taking the transactions and converting them to the ones and zeros that the TUT understands, and the monitor's doing the opposite. UVM is more complicated, basically. In fact, one of the first UVM courses I ever did, I had a customer on the course, and he came up with like an advertising slogan for UVM. He said, UVM, it's always more complicated than you think. And it is. It's complicated. I'm not trying to put you off, because the upside of complication is it's powerful as well. And in the bottom right-hand corner of this the screen here, you can see that there's a block there called sequencer. I don't know why I'm pointing to it, because you're online, you can't see me. I'm trying not to do that. I'm trying to use words to describe things. There's a block called sequencer, and that is the thing that's generating transactions. So the more basic methodologies, the transactions were really being generated by the test. Now we have a separate component, a separate piece in our test bench that just generates transactions. And in UVM, we wrap all of those up in a thing called an agent. And an agent has a a sequencer that generates transactions and a driver and a monitor. And the reason why we do that is it's a really useful piece of reusable IP. So you'd have an agent per physical interface on your design under test. So if you had like an AXI interface, you'd have an agent for that. If you had an I2C interface, you'd have an agent for that, etc., etc. And if you had multiple of the same, well, you just have multiple identical agents. But UVM adds loads more than the more basic methodologies that I showed you. So we've got other things going on here. We've got what's labeled register layer. Most chips have memory map registers, and rather than in your test saying, please write 123 to address 456, which is bound to be wrong when somebody changes something, and oh no, that register's moved to address 789 now, and you have to go back and modify your test. The register layer is what's called an abstraction layer that sits in between and means that you can write, please write mode 3 to the mode control register or something like that. And if that mode control register changes somehow, yes, of course, you've got to update something in your code, but only once rather than a zillion times. And there's other things going on here. Scoreboard is a checker. A virtual sequence, is a embedded controller. So rather than just having a test, we might have lots of things controlling things. It's just basically much more complicated. ConfigDB is a way of configuring the test bench. So you either for your particular DUT or for that particular test, right? The number of transactions you generate, the type of transactions you generate, the width of whatever. It's a database that you basically write into from high level up, probably the test, and the different components read out of. And then finally, factory. This is an implementation of what's called the factory pattern. I'm telling you that because if you know what the factory pattern is, you will see that this is, as I said earlier, this is big boys and girls software engineering. We're a long way from hardware design now. We're doing proper software engineering here. And so if you don't know what factory pattern is, it's a way of doing object-oriented design, basically. And then you can see right at the top, we have the test. And the test is the same as what we've already talked about. And the whole of the test bench is instantiated in the test. So you might have one or a small number of test benches. So everything on this slide, apart from the test, well, not the factory and the ConfigDB actually, but all of the stuff where it says reusable verification environment, that would be then instantiated many times, once in many tests, basically. And all of this stuff, I haven't said this yet, is classes. So SystemVerilog is object-oriented, this is object-oriented, and all of this is made out of classes. And if you know about object-oriented design, you'll know what a class hierarchy is. I can't really teach you object-oriented design this morning, but you can see there's lots of inheritance going on. So that class on the left there that says UVM sequence item, that's the base class for transactions. In other words, we're going to make transactions out of that. If you've not seen object-oriented design before, hopefully when you see the code, it'll explain it. You can see underneath that it says sequence. A sequence is a bunch of transactions. You can see in the middle it says UVM component. That's the sort of generic, like what's called the base class of, you can see underneath it, it says UVM driver. You use that to make a driver. You use UVM agent to make an agent, UVM test to make a test, etc., etc. It's test bench Lego, basically. And you can see lots of other classes for doing other things. And also in UVM, there is a time dimension. There's a time element. So because we're making our test bench out of classes, at time 0, nothing exists. In VHDL, once you've compiled your code, everything exists. Whereas in UVM, all of these pieces of our test bench are now made out of classes. So the first thing we have to do is create them, what's called construct them in object-oriented design. So we create our test bench, and that, of course, that needs to be the first thing we do. And these things called phases are different stages of running your simulation. So the first one is called the build phase. The next one is called the connect phase. And if you look at the animation, that's where we connect the pieces together. Let's ignore the next two. And then the next important phase is called the run phase. And the run phase is where the simulation actually runs. And then there are 4 more phases at the end, which we'll ignore because it's always more complicated than you think. And you can see on the right there, those so-called runtime phases. It says it's even more complicated, but we haven't got time to go into it. The key thing about phases is they control the order in which things happen. You can't connect up a non-existent piece of your test bench, so you better make sure you've created it before you try and connect it up. How can you do that? Well, one way of doing that is to make sure you create the piece of test bench in the build phase and you connect it up in the connect phase. And because the connect phase is guaranteed to be after the build phase, the order is now guaranteed. So that's what phases are for in you. So as I keep saying, it's a lot more complicated now. There's a lot more slides in this presentation about it. Another thing to talk about is the idea of transactions and sequences. So a transaction in UVM, it's often called a sequence item, but it's a transaction, is now a class. So we've seen a task or a procedure call. We've seen a record type in VHDL. I didn't say that's the same as struct in Verilog or in C, basically. In UVM, a class is used for representing a transaction. And then we have this thing called a sequence, which is a bunch of classes, and you can have sequences of sequences and sequences of sequences of sequences, and so on. And what we're going to do, I'm going to show you about 5 slides now of UVM code very quickly, and we're going to put a basic test bench together like that. And I've realized when I was practicing this morning that actually there's one more component that's going to be shown that isn't on this diagram, which is a checker. We're going to put a checker in as well. So we're going to have an agent, we're going to instantiate that in something called an env, and then we're going to have a test. We're going to, well, I'll show you briefly how it connects to the DUT as well. So here's our transaction. So there's a class that comes with UVM called a UVM sequence item, and this syntax here extends. If you know about object-oriented design, you'll know what is going on here. If you don't know about object-oriented design, we're taking this class called a sequence item, which is the generic transaction class, and adding some more stuff to it. We're creating a WB trans, which is a kind of sequence item. And you can see we've added some transaction looking data members to it, an address, a data, and a kind. Kind is basically read or write. So there's our transaction. And here's our sequence. And as I just said, a sequence is a bunch of transactions. You create a sequence, or sorry, you code up a sequence by extending a UVM sequence base class, parameterized, if you know what that means, to the kind of transaction we were dealing with. WDB trans was our transaction. So this sequence can only generate that kind of transaction. And when I described a sequence as a bunch of transactions, it's not like a passive thing. It's not like a list or an array or something like that. It's actually some code that generates transactions. So you can see we've got a task here. We met tasks before. They're like VHDL procedures, which is generating 10 random transactions. I'm not going to explain the syntax in general. That's just SystemVerilog. This is all just standard SystemVerilog, but the classes come free with UVM. And this UVM do with business, you can see it's clearly seems to be generating some kind of transaction, doesn't it? And you can see that we clearly seem to be generating 10 transactions. And what calls this body task? Well, the UVM source code. The UVM source code handles all of this, and so this task will get called at the right time to generate our 10 random transactions. Here is some of the code. By the way, this is some of the code for the sequence. This is some of the code for the transaction. Here is some of the code for the driver. So you can see again, we're extending, we're basing our code on something that we get free with UVM. And we're overriding a task called run phase. This is going to get called by the UVM source code at the right time. Guess which time? During the run phase. So that's how you make things happen in different phases. You override a task with the right name and it will get called automatically by the UVM source code. Well, some of them are functions, but let's not worry about that in case you want to be pedantic. So you can see what's going on here. We've got a loop that goes around forever. We've got a line of code that seems to be getting a transaction. We're calling a method called getNextItem on something called seekItem port. What is that? Well, that's a piece of UVM. The port is how UVM connects the components together. So this line of code here is going to output a random transaction. Where did that come from? Well, via the UVM source code, it came from the code you just saw on the previous slide. And then you can see, depending on whether it's a read or a write, we're either calling a read task or a write task. And the code inside those tasks is pretty much the same as the code that I showed you. It's probably about 50 slides ago now. So, and then we signal back to the sequence that we're ready for the next transaction. That's what's going on at the bottom there. So you can see it's the same thing is going on, but now it's more complicated. It's just the same thing, but in a more sophisticated and powerful way. We need to stick together our driver, monitor, and sequencer to make an agent. So what's the difference between a sequence and a sequencer? It's actually the sequence that generates the random transaction. It's the sequencer that handles the communication with the driver. So that's when you're learning UVM, there are various things that you have to get your head around. And this is one of those things. What's the difference between a sequence and a sequencer? And here you can see we've overridden. So we're inside an agent. We're making an agent. You can see that at the top of the slide. We've got instances of a monitor, a driver, and a sequencer. So they're just data members of the class. And then we've overridden a method called build phase. I've used this word method. If you don't know object-oriented design, a method is some kind of function or task that is part of the class, basically. So we've overridden a method called build phase. So that will get called by the UVM source code in the build phase. And you can see we're creating the driver, the sequencer, and the monitor. You can also see that it feels like you've just been hit in the face by some code if you're not familiar with this, because my, doesn't it look complicated? Yes, it does. It's esoteric stuff. I'm not trying to put you off. As I've said already, the upside of this is it's really, really powerful. So we're creating the three things in the build phase, and then you can see there's another method we've overwritten at the bottom called connect phase, and we can see, I'm not going to go into detail, but clearly we appear to be connecting some things, don't we? And we're connecting, if you look carefully, we're connecting the driver and the sequencer together in the connect phase. So just giving you a taster of what's going on. The next level up is something called env. I've not mentioned that, but an env is like a DOM layer of hierarchy in UVM, and we're instantiating our agent and our scoreboard. Scoreboard is the checker, and I haven't shown you the code for that. And we're creating them in the build phase, and we're connecting them together in the connect phase, so that the monitor is the agent is outputting transactions, and they're getting checked by the scoreboard. And then here's our test, and the test is a class as well. And you can see that the env is our test bench. We are instantiating that in the test. That's what you do in UVM. But you have many tests, each with the same env instantiated in them. And in the build phase, we're creating the env, just you do the same thing at every layer of hierarchy. And then we've got a task called run phase. And now it's significantly different to the test that we've seen before, because we're not doing a write, we're not doing a read, nothing like that. We're not outputting any messages. That kind of stuff was being done by the sequence. what we're doing here is starting the sequence running. So we've got a sequence. WRAM sequence was the name of our sequence here. You can see that class WB-RAM sequence. So we're doing the same kind of stuff. We're creating it. Ignore the objections. You need that, but haven't got time to go into that. We're creating the sequence. We're randomizing it. So that needs doing. And then we're starting it running. And it's actually the sequence that's generating 10 random reads and writes. So broadly speaking, it's similar, but you can see it's much more complicated and it's much more powerful, basically, and things are a little bit different now. And then finally, just to stitch it all together, you need a module. So if you don't know SystemVerilog, a module is the equivalent of an entity in VHDL. And you can see now we actually have an instance of the DUT, because we need that, of course we do. It's a test bench. And this initial block at the beginning, we're calling a function now called run test. And basically, at time 0, some code, the initial block runs, and we call into UVM world. So nearly everything we write in UVM is in some class or other, and the actual module-based stuff is tiny. We need to instantiate our design and test. We need to call some function to transfer the execution into the UVM source code, basically. And after that, we're now in UVM world. So same idea, broadly speaking, but much more complicated. Something else you could do is use a different language. So even if your DUT is in VHDL, perhaps you're doing an FPGA, doesn't mean you can't use SystemVerilog to do your test benches, because SystemVerilog, especially in combination with UVM, is very, very powerful. But another thing you could do is use a completely different language. Why might you want to do that? Well, SystemVerilog takes you 5 days to learn, and UVM takes you another 4 days to learn. And we would be very, very happy to sell you a training course. Of course we would, because it's what puts food on my table, and you're very welcome. Our courses come highly recommended. But perhaps you don't know, you don't have the resources. That's not what you want to do. Perhaps you already know Python. And so what you could do is use something I've called CocoaTB, which is a way of doing all of the same things that we've just been showing you, or I've just been showing you in UVM, in OSVVM, in UVVM, but this time doing it in Python. And we are just developing a CocoaTB course as well. And so here is exactly the same thing, except that the test bench is now written in Python rather than in VHDL or SystemVerilog, though the DUT itself has to be in some kind of hardware description language. And here is a write function written in Python. So you can see that there are similar things going on, even if you don't know Python, and I don't know Python very well, but I was able to write this code. And the key point is you can see things going on that are similar to what you've already seen. So we're driving an address, we're driving a data, we're waiting for, or appear to be waiting for the rising edge of the clock, and so on. And we've also got a read function here. So this is doing a read, and it's outputting some data. You can see it's returning some data at the bottom of the slide. So again, same idea as we've seen again and again now this morning, but written in Python. And here's our test. And you can see that we've got some sort of housekeeping-y stuff, but about halfway down, we've got a for loop. And we're calling our write RAM function, which is the one you've just seen many, many times. And then we've got another for loop, and we're calling the read function many, many times. And you can see that the if statement about 3/4 of the way down, we're doing some checking there. You can see we've got an array. So the array, as we saw many, many slides ago, is our reference model. But the key point is it's exactly the same idea, but written in Python. And I wrote this, even though I don't know Cocoa 2B very well, and I don't know Python very well. So, you can do it, and it works. And it's available on EDA Playground. If you're familiar with EDA Playground, make a note of that URL there, and you can play with it. And so the code on this slide is the very top level. This is the code that, if you like, is executed by your operating system that sets it all going, basically. So same thing, but done in a third language. Now it's going to get quite esoteric. Come in.
Is that the one on Cocoa TV, yes?
No, that's in the main hall.
Is it the main hall?
Yes.
Thank you. Thanks.
Excuse me, people online. Just had someone come in the room. So this, I really like this language. There's a language called PSS. It's still quite esoteric and forward-looking. It's been around a while, actually, and I think it's really, really cool. Might be a step too far, might not be. If you're already using UVM, you might think, oh, yeah, this looks cool. What is it? It's the Portable Test and Stimulation Standard. It's an Accelera standard. And to explain what it's for, I'm going to change DUT now. Here's our DUT. It's some kind of system on chip, some kind of SoC. And if you have this SoC, you might want to write a test that takes information in through the Wi-Fi and writes it to RAM. And then you might write another test that takes information through the 4G modem and writes it via the DMA to a RAM. This one was using a CPU. Another test, you write information from the CPU to the display. And then you might think, oh, better make sure that we can do two of these at once. So can we take information from the Wi-Fi and write to the display at the same time? Can we take information over the 4G modem and write and the Wi-Fi at the same time? We might need a test to write, can we do all three at once? Key point is here that we've now written 6 tests. Those tests are probably random. We've probably picked random addresses in the RAMs. We've probably picked random channels, or I don't know a lot about 4G, but random configuration on that, random channels on our Wi-Fi, picked a random part of the display. The data that we've written is probably random, but we've still had to write 6 different tests. What PSS does is, instead of you writing those individual tests, what it does is you tell the language, you tell the tool about the system. You say, well, we've got, 3 CPUs, 4 CPUs, we've got 2 DMA controllers, we've got a display, we've got a GPS, we've got a CDMA. And then you tell it things like, well, we can only do this 4 times in parallel. We've only got one of these. This has to be done before that. You enter all of that kind of stuff into PSS, and then it writes the test. So you wouldn't write these 6 tests, it would write these 6 tests. So it's the next step. My ex-colleague, because he's retired, John Ainsley, one of the founders of Doulos, calls it randomization on steroids. It's another level of randomization. It's not just randomizing details about the test. The whole idea of the test is random. So I'm just going to show you a bit of a PSS code, and I'm going to use a simpler DUT because otherwise your brain will explode. So we're going to have 2 memories and 2 serial interfaces, SPI interfaces, and the low level, the actual test bench itself, is going to be UVM. So we've got agents. So we've got 2 agents pretending to be CPUs. We've got 2 agents pretending to be these SPI interfaces. And you can see here is some code, and you can see that PSS has packages, if you know what those are, and you can see this keyword resource. So we're representing the DUT. We're representing the CPUs, the memories, and the SPI interfaces. So I can't go into like loads of detail, but you can see what's going on. We're representing the DUT. Here is a component that's representing one of the SPI interfaces. And you can see it has state, and initially it's not set up. more on that story in a minute. Here is something called an action, because of course, at the end of the day, we want a test to run. We want things to happen. And so this is an action called setup SPI. And you can see that in order to do that, we need one SPI interface. Of course we do, because we're setting it up. We need a CPU that's going to do the setting up. And we're going to output the fact that we've set it up. We'll see that in a minute. And we're going to output the fact that, well, same thing, doesn't matter. Then at the bottom, key point, we've got a function that we're calling, and this is actually going to call into UVM. So your tool will organize that for you, basically. So this FPI setup is indirectly going to start a UVM sequence running on a sequencer that generates the traffic, the transactions, to set up an actual SPI interface. So we'll come back to that. Another important construct in PSS is something called a buffer. And you can see it has a size and an address. But the key thing about the buffer is it must be written before it's read. And so this is what's called a scheduling construct. So I mentioned a few slides ago, we're going to have to organize that something happens before something else. And a buffer is a key part of how you represent that requirement in PSS. So here is a component. A component is just a dumb layer of hierarchy in PSS. Here is a component that's representing the CPU, and you can see we've got an action called CPU to mem, which is copying information from the CPU to one of the memories, and you can see it's outputting one of those buffers. So just remember that. And you can see it's got this thing called an exec body, which is calling a function, and that function is going to be interfaced to UVM, and a sequence is going to get started that does this in UVM. And here's another action called mem to SPI, which is going to copy information from a memory to an SPI interface. And the key point I want to make here is notice that the same kind of buffer, burst_b, which is our buffer, there is now an input. And that forces this action here, copying information and data from the CPU to the memory, to happen before this action, copy from the memory to the SPI. Because of course, if there's nothing in the memory, you can't output it through the SPI. And then we've got a function that actually does that as well. So can you see that we are building in information about, or representing information about the DUT? And so then we've got our top level. Here's our top level. And there's loads more code than this. I'm just giving you a taster. And we've got something called a pool. And n CPUs is just a constant, the number of CPUs we've had. N mems is the number of mems. N SPIs is the number of SPIs. A pool is a bunch of resources. And you can see we've got an action at the bottom. And inside the action, we're calling some other actions. So mem to SPI and 0 and 1 are instances of the mem to SPI that we've just seen. Sorry, gone back too far. It's this one here. And what we've said is in parallel, we want to do 2 memory to SPI writing. But if you remember, something needs to write the because of that buffer, something needs to write the information into the memory. But we haven't said that. But PSS knows that. Also, the SPI can't do anything until it's set up, till it's configured. And I haven't shown you much of the code to do that, but I just showed you a little bit of it. The tool, because of the PSS that I've written, the tool knows that in order to do these activities, some information needs to be copied to the memory, and the SPI needs to be set up. So the tool, when it writes a test, it knows about those constraints. And so one thing that the tool will do is then represent like a sort of flowcharty thing like this. And the 2 dark blue things are the activities that the actions, that we specified. And the light blue ones are ones that are inferred. The tool has worked out, because of the buffer and because of the state object that you saw very quickly, the tool has worked out that we also need to do these other things. And so the tool has written the test. And If you look carefully, you see we've got the WB to mem, which is one I did show you, and SPI to mem, which is one I didn't show you. So the tool has decided where the data comes from. It's writing much more random tests. So it's the next layer of randomness. So that's what that's what PSS is. We need to talk about static verification. So for the last hour, I've been talking about dynamic verification. We've been executing code. Static is just statically analyzing your design. So something that's been around at least 25 years is what's called logic equivalency. We had a problem. The synthesizer synthesized the wrong thing. It took us ages to debug. We eventually realized the synthesizer had synthesized the wrong thing. And from that day forth, we ran logical equivalence checking. We just compared our gates and our RTL. So it's not new technology. It's relying on your gates being not too different from your RTL in terms of timing and things like that. A fancier version of the same thing is called sequential equivalence checking, and this is fancier. It requires what are called formal verification now to do designs that are much more different. So you can see that you can compare RTL to RTL or RTL to some high-level C model or something like that. So to do this kind of thing, you need a formal verification tool like Questa Formal, VC Formal, Jasper, and so on. So formal, a very, very powerful idea, and we'll come back to that in a second. I didn't explain what verification was. Verification is checking that the current stage is the same as the previous stage. Previous stage could be the specification, or it could be the RTL if you're checking gates and so on. So one of the things that you ought to do is check the timing of the gates, so a very low-level thing to do. So the way that works is it adds up the delays along all of the different paths in your design and make sure that they're not too long or too short. And hopefully most of them are all right, but if some of them are not right, then it will output a table saying, well, all of these delays add up, and they add up to 20.1 nanoseconds, but your clock period is only 20 nanoseconds, matey, and so you've got a problem. And so that's a sort of low-level thing, but we're not executing any code now. This is static. We weren't executing any code when we did the logical equivalence checking or the sequential equivalence checking. So what about formal? Formal is really cool. Formal is mathematically proving that your design is correct. So again, we're not executing any code. So what we do is we write rules, and you can write rules in Tickle, or you can write them in a language called SVA, which is part of SystemVerilog. And some of the rules are assumptions, so you need to say what are the legal inputs. So we've got some assumptions here saying that for the data isn't going to change. We've got two different addresses. So we've got one address that's going to be different to another address. You'll see why that is. The address isn't going to change, and ignore I. That's just low-level detail to do with the design under test, not to do with formal. But by the way, we're back on our memory. We're back on our wishbone memory again. And then, well, I've just told you that. We're back on our wishbone memory. And then you can write rules like this. So if you look at the top, we've got this construct called a sequence. And you can see it's got an input, is some address and some data, and ignore the SEL. And you can see that it's driving the address input. So WB address is the address input on wishbone with the address, and the data with the data, and various other controlly handshaking things. And we've got a sequence for reading, and it's doing the same thing, but you can see right on the right hand side of the slide, WE is high for the first one and low for the second one. And then the key point is the third thing down, we've got a property. And that property is using those two things called a sequence, and it's saying we're doing a write. Well, basically, if you look at the right-hand side of the slide, that arrowy thing, that's called an implication operator. It's a really, really powerful operator. And it says, basically, it says, if the left-hand side is true, then the right-hand side should be true. So what we're saying is, if we do a write, followed by a write or a read to a different address, because we've said that A and AN must be different, and we do one or two of those, and then we do a read from the original address, then the data should be the data that we wrote. I can't go into detail of the syntax, but that's what that's saying. And the key thing is the formal tool will prove that that is always correct, whereas the simulation will just do it for the particular address and data that you happen to choose. Where we said for all possible combinations of writes with another couple of writes and reads in between, and then a read, it should work for literally any data address. Any address, any data, any. This is quite complicated. It has byte lanes, so you know it's anything. It will always work. And we've got another couple of properties here which are checking that the RAM is outputting the acknowledge signal in the right place. And again, what the formal tool does is it mathematically proves that that always works. With simulation, it depends on what simulations, what tests you happen to write or happen to run if they're randomly generated. Whereas now it's testing literally every possible simulation. How cool is that? Really cool, really powerful. We run courses on that as well. So a really, really powerful technique. And your formal tool will tell you which one of your assertions have passed and which ones have failed in some kind of table. This is the Cadence tool, but the Siemens tool and the Synopsys tool do exactly the same thing. And they also, with your formal tool, you get a whole bunch of other what are called apps. So formal property checking was what I was just showing you. You can get an app that automatically generates properties based on your source code. Sounds very incestuous, actually isn't. Does things like checking array bounds and overflows, things like that. There's coverage analysis. So not did I execute this line of code, but is it even possible to execute this line of code? If it's not, probably you've got a problem. Other apps are listed there. So, you know, is it possible for X's to get to the wrong place? Is it possible that two things can talk to each other? Is it possible that my keys can leak out of the part of the chip where they're being stored, and so on? And as I mentioned before, sequential equivalence checking is to do with formal too. So that was just a quick trip around the verification maze. I was just showing you lots and lots of different ways of doing verification, a smorgasbord, if you like. And I work for Doulos, as I said at the beginning. We are a training company. Our product is training. We offer training courses on everything that I've just been talking about in this presentation, and lots of other things besides. So language training, SystemVerilog, VHDL, and all of the things in the slide, System C, lots of stuff on embedded software, and lots of stuff on related things like Python and AI, deep learning, and things like that. So finished 9 seconds early. Thank you very much for your attention. Just out